Okay. So thank you, Lionel, for being here, which is a real question. And wait, I have to make something to. Where is the story? Ah yes, partage l'écran. So I let you go. Okay. So yes, sorry, I have to let people enter the room. Sorry. Wait, I will do it from my computer, from my telephone. I think it may be more easy. Okay, I let you begin, and
yeah,
because yes, that's on YouTube. That's recorded. But I have to deal with the people entering the room. So. That's okay. So sorry. Okay, so thank you.
Thank you, Paul, for the organization of this event. The talk that I will present concern an important topic in ecology. I will not say that I started to work on this topic for the conference, but it is almost the case. I started to investigate how can we model some absence presence data in a dynamic way using a time series framework. So to change the slide, how would it work?
This one. Wait. Sorry.
Okay. So what we call absence presence data concerns the absence presence of a species in an ecosystem, which is a problem which is widely considered in the literature in ecology. So typically, it is connected to some abundance data, because you have some the number of individuals for some species are recorded, and sometimes you have a non-negligible amount of zero, and then you are just interested in the presence of or the absence of the species of a given species in the ecosystem. So the data can be collected at a different location. And also at different time points. And then the goal is to explain, to try to find some determinants, some variable that can explain this binary vector of 0 and 1. So one of the interesting questions is how to model this type of data, especially across the time. And also to identify some possible patterns with, for instance, the attraction, the within dependence between species, the influence of the environment, and the time dependence. So the main point is that if you consider time series analysis, it is not so common for this kind of data. So we don't have a lot of model for this. And especially if we want to combine some data that are collected across the time, and at the same time, collected also across several observation sites. So I will provide the motivation through an example with a paper published in the proceeding of the Royal Society, and which concern some waterbird surveys that are considered in a set of irrigation ponds. So ponds in French means un étang. And in this paper, people are interested in explaining the absence presence data of 7 waterbirds, and they use many covariates for this. So they use some fixed environmental and spatial covariates. So that is the characteristic of the pond. They use also the information about the presence or absence of some specific vegetation. And they also consider the absence or the presence of the same species at the previous time, at time t-1, and also some another type of information, the absence presence of other species at the same time. So if you look at this kind of approach, it's quite complicated because we use a lot of information, a lot of different information to explain the dynamic. And well, this is.
What is the time scale today?
Okay. So I think that it is in the this kind of data. I think it is every during several years you have one record per year.
Oh yeah.
Yeah. It is in this example. Okay, so it works like this. Okay, so what are the main questions? So the question is how to develop an autoregressive time series model, because if you want to model the influence of past values of the presence or absence data on this influence on the actual presence absence data. The second question is how to get some statistical guarantees when you use a time series framework, but combined with a longitudinal analysis. And I will take the models that were used was used in the previous reference, which is called the multivariate logistic model. So it is a typical model that you use, especially in econometrics, to model binary data. So the absence presence, the 0, 1 is modeled by the Y, the response is simply 1 if a continuous response is positive. And this continuous response is a linear combination of some covariate plus a noise. So in the example here, the noise is modeled through a multivariate Gaussian distribution in such a way that marginally it follows a logistic distribution, and then marginally the model is a logistic regression. So that is each coordinate conditional on the past satisfies the logistic regression. So this is a standard model for this. Another variant is when the logit function here is replaced by the inverse of let's say the inverse of the cumulative distribution function of the Gaussian. And in this case, you simply obtain a multivariate Gaussian distribution for the noise here. So this is the model, the multivariate probit that I will study, but the study can be also extended to the logistic case. So you have still this problem. Okay. No, it's okay. It's okay. So what we do in this work, we present a time series analog of the multivariate probit model. We try to investigate a frequentist approach for parameters inference, something which is not automatic and not so easy to find some stationarity properties for this model. So I will precise that at this point, stationarity property are interesting mainly for deriving some limit theorems. For the long-term behavior of the presence-absence spaces, we will not be able to model the extension of something like this. So this kind of approach is mainly interesting for the short-term interaction. So you can simply identify which quantity has an influence of the presence data, but you cannot, of course, model something which will be non-stationary, especially during the long term. We try to adapt this the single pass framework to the longitudinal approach. And we will start with the single pass analysis. So we start with the existence of stationary paths. So here is the model that I consider. So the y at time t and for the species I is given by 1 if and only if lambda plus the epsilon it is positive, where lambda t is a linear combination of past values of the absence presence data plus a linear combination of some covariates. And the noise is simply a multivariate Gaussian with mean 0 and correlation matrix 1. So what we assume is that the noise and the covariate process is assumed to be stationary, which is something which is classical. We assume that epsilon at time t is independent from the past information of the noise and of the past value of the noise and of the covariate. Something which is important, the process xt is not required to be ergodic. This will be important in the longitudinal case because we put some covariates that sometimes are fixed across the time, and then we don't want to use specific ergodic process. For instance, you can have this decomposition of the covariate process. You can have a fixed covariate and a time varying covariate. So typically Z is the point characteristic, if you prefer, in the example, and WT, for instance, is the meteor's temperature. Okay, so if you don't consider the covariates, there is no problem for deriving stationarity property for the following reason. We simply have an irreducible Markov chain Okay, because since the Gaussian distribution has a full support, the probability of reaching an arbitrary binary vector is always positive, whatever the previous value. So all the transitions are positive, so there is no difficulty. It's a bit more tricky if you put some covariates inside, but intuitively the result should remain the same for the following reason. Since epsilon t is always independent of the past information, whatever happened in the past, the probability of reaching another vector, an arbitrary vector of binary value, is always positive, and then we should have exactly the same kind of recurrence property. What I do to study this, I use something which is called a random mapping. So if you consider y at time t, that is a binary vector, you can always write this. It is an indicator function, so a vector of indicator function, but it is simply a function, a random function, which depends on the covariate end of the noise of the previous binary vector. And then if you want to find some stationary solution, one classical approach is to run the backward iteration. So that is, you run in the past some iteration of the process, and you show that when S goes to infinity, you obtain something, you obtain a convergence, and the value will not depend on the Y value, which is the initial value. So of course, when you use the categorical data, convergence has a special meaning. If you have a finite number of value, everybody knows what convergence means. It means at some point you are constant. So we just have to show that this kind of iteration after some point for large value of S is constant. So I have a special argument for this, which is a coalescence argument. So if you consider the following event, first I will start with the ergodic case with p is equal to 1 and 2 spaces. So if you consider this event Ct, so the event Ct, which is written here, when this event occurs, it means that whatever the previous value of the binary vector, you are sure to obtain a binary vector which is always, all the coordinates are equal to 1. Okay, so from the ergodic property, the probability of this event is positive. Then when you run back your iteration, you wait the first time until this event occurs. When this event occurs, it is not necessary to run back again the iteration. Why? Because whatever the previous value, you will see all the paths which will coalesce through this state. Here it is a state 1, 1. Okay, so here at this point, you already have the convergence of the backward iteration. So there is no condition for stationarity, which is expected, because the noise has full support, and we recover this when you use this kind of argument. So if you are familiar with the simulation of Markov chain, you probably recognize the Prop and Wilson algorithm for perfect simulation of linear probability measure. And this is the idea that I use here. Okay, so this gives the following result. So when the process is not ergodic, the X is not ergodic, one can still show that the probability of this event conditional on the invariant sigma field is always almost surely positive. And then you have also this kind of recurrence properties. So it's a bit more technical, but it is exactly the same idea. And for larger value of P, it is also the same idea. So let's admit this. And then you obtain the following results. There exists a unique stationary and FT adapted process, solution of this recursion. You automatically have the Bernoulli shift, what we call Bernoulli shift representation of the solution. So in terms of past, present and past value of the noise and past value of the covariate. And from this representation, when the process is ergodic, you obtain also the ergodic property of the Y process. So this solves the problem of finding some stationary and ergodic solution for this type of dynamic. Okay, so now let's discuss the inference of the parameters. It's a bit tricky. If you remember the talk of Julien Chiquet yesterday, it was a bit the same problem. When you take this kind of multivariate discrete distribution, you have a problem of likelihood expression, which is quite complex, with several multiple integrals that you have to compute. It is the case also here. If you consider the probability of getting an arbitrary binary vector conditionally on the past, what you obtain the integral of the Gaussian density the number of integrals is equal to the number of species, and this integral is taken on some rectangle involving the parameter. So it's quite difficult to optimize this, and the log likelihood has this following expression. So as it was discussed in the talk of Julien yesterday, the numerical analysis of this is difficult, so you have to take some very specific techniques. In this talk, I will totally avoid the numerical difficulties. I will not use the likelihood, but I will use the pseudo-likelihood method. This is why I asked the question yesterday after the talk, because I use this kind of approach. So what we do, we first estimate the regression parameters, that is the parameter in the lambda. And to do this, we assume that there is no correlation in the noise component, that is in the Gaussian random vector. If it is not the case, it's not important. So it's simply the likelihood under a wrong assumption. But in fact, it works. It's sufficient to identify the parameter. And this is a classical example of what is called a pseudo-likelihood method. That is, it corresponds to the likelihood under a very specific scenario of independence. So what is nice here is that when you look at this kind of equation now, the coefficients involved in the different equation, that is across the I index, the coefficients are not the same. So you can estimate all the coefficients separately, or the line of the matrix separately. So you have a kind of what we call estimation, equation by equation estimation. So it's very fast to estimate parameter using this kind of approach. In the second step, we simply plug the pseudo-likelihood estimator of the first step. So not in the expression of the likelihood, but we use a pairwise likelihood. So simply, you can just compute the probability of a pair. It is you compute the probability to take two value 0, 1 for the species I and the species I prime, conditional on the past. So you obtain an expression of this probability, and you take the sum, and you take the log of the sum of the log, sorry, and then you optimize this. So it's, once again, it's not the likelihood method, but it's called the pairwise likelihood method. It's an example of what is called composite likelihood method. And in fact, once again, we can show that you can estimate, you can identify the parameter like this. The advantage is that now we only have here in this second expression one integral to compute instead of k integrals, and then numerically it's more tractable. So at least it works in theory under some classical assumption. If I have I have a second moment and a classical assumption of compact assumption for the parameters, up to an identifiability constraint on the covariate, it's a linear independence, but it's not very costly. We have strong consistency and asymptotic normality for all the parameters. So what is a bit surprising here is that for getting asymptotic normality of the correlation matrix of the Gaussian component, I have a very, very demanding moment assumption. This is because when I compute the score and when I want to show square integrability of the score, I have the ratio of some integral, and I cannot simplify the things, and I have to use this kind of assumption. I don't know, maybe it's not optimal, but I didn't find a way to remove it. But since kappa can be arbitrarily small, at least you can put a Gaussian process in the covariates. At least it works for unbounded process. For instance, if it's Gaussian or not Gaussian. Okay, so this gives a theoretical result for this kind of estimation. Okay, so now I just forgot to precise something. For the models that we use, what is interesting in this kind of model, and I think it is the advantage, is the interpretation that you can do with the data. So I just precise that here. I mainly present the theoretical part, and I did not investigate the data for the moment. But what is interesting with this dynamic is the interpretation that you can make. For instance, when you have some positive or negative sign here in the matrix AG or in the matrix B, it measures if the absence presence of a species at a previous time have a positive or negative influence in the presence or absence species of the next time for all the species. And it is the same for the covariate. The sign of the B coefficient measure if the covariate has a positive or negative impact on the presence. At the same time, the correlation between the noise component means that either you have a positive or negative association between the binary vector, between two species. So it's a measure of simultaneous dependence. And this, again, depends on the sign of the coefficient in the matrix R. So this is very easy to interpret the inference result, which is one of the advantages when you use this kind of okay. So now let's discuss the longitudinal approach. So in the longitudinal approach, I will use a multipass analysis. So I will try to be quite close to the application that I showed at the beginning of the talk. So now I suppose that you have several observation sites. So some points in the example. At each point with the letter J, at point J, I suppose that I have the absence presence data model, which is given as in the previous form. And then I assume a very simplistic scenario, that is the coefficient are all the same for all the points. So all the assumptions that I will make are very simplistic, but it is first to see if you can prove something mathematically, if we have some statistical guarantee, and it was the first step. So probably that we can complexify it, but at least at the beginning, I wanted to investigate some very simple things. So for instance, there is no individual effect. What you call individual effect, that it is the model is a bit the same at every point, at every observation site. For instance, in the literature of longitudinal data or panel data, the intercept sometimes depend on the individual. It is not the case here. And what we want to get is an asymptotic result for parameter inference. Under the scenario, which is the most challenging, we assume that at the same time, the number of individual n goes to infinity, and the number of time points, capital T, goes to infinity as well. So when one of these quantities is fixed, it's easier to prove some result, but I prefer to solve this kind of approach when you have more and more data across the time and at different locations. So I investigate two scenarios. So in the first scenario, I decompose the covariate as follows. I have a fixed part of the covariate which depend on the observation site J, but not on the time. So this is typically the characteristic of the observation site. And then I have a time varying covariate which depend on the site J. So typically, I use a very simplistic assumption. So I assume that there are many independence assumptions. So the fixed part is independent from the time varying part and independent also of the noise. So the single dependence is for the process Wj, which is assumed to be an ergodic process. But of course, it is not completely meaningful if you sample the data at some locations that are close from each other. In this case, you have a dependence between the sites, which is not covered, of course, by this approach. So it's a very simplistic approach, which is probably a bit meaningful if the sites are far from each other, but when there is no dependence, it's not really a spatio-temporal modeling. The second scenario, I assume the existence of what is called common factors. So there is a dependence through common factors. So I decompose the covariate in the following way. So I have some site characteristics, and I have a time varying covariate, but now this time varying covariate is the same for all the sites. So for instance, you can put a kind of macro variable, some global warming index, something like this. And I did this because I found that there is a different behavior for the estimation between the scenario 1 and the scenario 2. And once again, the W process is an ergodic process, and I have also many independence property for convenience for stating the results. So when we want to study the parameter consistency, typically we only need the lower large number. So here we work with some variable that represent a stationary random field due to the independence assumption and the stationary of the covariate in time. We have a process which is indexed by 2 parameters in the partial sum of the pseudo-likelihood method. And typically, we have this kind of representation of the functional. And then it simply remains to get the low large number for this kind of stuff, which are typically stationary for the double indices. So there is a result. So at least for the 2 scenarios, under some specific moment condition, when both quantity n and capital T goes to infinity, the partial sum will converge to the expectation. So typically, this result is related to an ergodic problem for random fields. So when you look at a spatial process or random fields, you have 2 indices, and then you have what we call the 2 actions on the sequence. You have the shift with respect to the first coordinate and the shift with respect to the second coordinate. And typically, the ergodic theorem says that at the limit, you have a conditional expectation. And the conditional expectation is taken with respect to the sigma field, which is the intersection of the invariant subset for each transformation. That is the shift for the first coordinate and the shift for the second coordinate. So what happened is the first scenario, we have IID assumption across the site. We have, in some sense, one direction for ergodicity, and then the intersection of one of the invariant sigma field is trivial, and then the intersection is also trivial. In the second scenario, where I separate the contribution to the J to the site and the contribution to the time, none of the transformation, that is the shift over J and the shift over T, are ergodic, but we can still show that the intersection of the corresponding invariant sigma field with respect to this transformation are also trivial, and then you still get this low large number. When you have this low large number, you take exactly the method that I introduced before. You simply take the sum of the log for all time and for all sites, and then you optimize this. You obtain some partial sum of this form. And once you have the low large number, it's sufficient to get the extension of the consistency result that I showed before for the single pass analysis. Okay, so it doesn't change anything in some sense for the consistency. So it's a bit different for the asymptotic normality. So typically, when you work with this type of time series model, which are defined in a conditional way, you have 2 ingredients. The first one is a low large number that is sufficient to guarantee parameter consistency. And the second ingredient is a result for martingale, in particular for sum of martingale differences, which appear when you take the derivative, when you take the score function. The score is a martingale. So it is also the same for the double summation when you use the longitudinal approach, except that the definition of the martingale is a bit more complex. There are several definitions of martingale when you work with 2 indices. So here I have the following martingale difference property for the partial sum that I investigate. So that is when I take the conditional expectation with respect to the sigma field at the previous time, but for I take the union over all the sites. So it gives 0, and it is also the case when I take the union of all the sigma field for the site, the previous site. So in some sense, you take the 2 direction, and then you have a martingale difference property when you take conditioning with respect to one half space or with respect to another half space. So in the first scenario, one can still show that if you normalize this partial sum with now the rate root nt, it has a Gaussian limit. So you can prove this directly because there are some independence property across the J, and then you can prove this using, for instance, simply the Lindeberg theorem for a triangular array of independent random variables. It's sufficient. It is more complex in the second scenario, In the second scenario, I have some common factors across the different sites. And here, in fact, one can show that the limit of Sn is no more Gaussian, but in general, it is a mixture of Gaussian distribution. And the second scenario is a particular case of a general result of Volny, who studied this kind of convergence. And the first case also is the particular case, but you can prove it directly. Yeah, so for the first scenario, one can still prove that the estimators are asymptotically Gaussian. For the second scenario, for all the estimators that I presented before, it's not so clear because here it's a limit in the univariate for the univariate H, and I have to find the analog for the multivariate case and then to translate this to the asymptotic distribution of the estimates. But I did not finish this for the moment, so it's still in progress to see what is the impact of this kind of result on the asymptotic distribution of the estimators, but of course there won't be a Gaussian. This is the result. And to get an intuition about this, look at this kind of decomposition that I make here. Okay, imagine that I take a double summation. Imagine that I take the Z, I multiply with the W. Okay, so you take the product Zj multiplied by Wt. You take the partial sum over the two indices. What will happen? You obtain a product of two partial sum. Each partial sum will converge to a Gaussian. And at the limit, what will you obtain? You will obtain a product of two Gaussian distribution. So this is a particular case of a mixture. So this is why when you take common factor, it's not expected to have a Gaussian peak. Okay. So what we can say about this type of results is that it is possible to develop a theory for time series analog of the multivariate binary model, and to take in account of many interesting situations with both endogenous and exogenous regressor when you study this kind of binary data. It is possible at least to find some numerically tractable inference method. At least theoretically it works. I have to check numerically if it is quite efficient in terms of estimation accuracy. And then it's necessary to study the finite sample properties of this kind of method. I did not do this for the moment. And what could be interesting theoretically is to use a more realistic modeling for longitudinal analysis. One thing which could be interesting is to put a spatial correlation across the site for the noise component, for instance, just to define a true spatiotemporal model, because here I assume some very restrictive independence assumption. But I have no idea for the moment how to combine this with the model that I define, and also to assume some more heterogeneity across the site with some variables that have a fixed contribution for each site, but at the same time, some of the coefficients can also depend on the site, which could be more realistic for real data. So these are some extensions that can be investigated. And I think I have finished. So I don't know if you have questions.
Yeah. Are there questions, comments? Ah, so are there questions? So, anything? Yeah. No reaction in the online public? No. Okay.
How do you see this?
I don't know exactly. Let's stop to share and see. So okay, no, apparently not. So I wonder, maybe we just did we thank you? I don't know.
Yes, one time, but you can do
Okay,
it the second time.
we can do it also a bit more if you want. Okay, so thank you very much, Janelle, and thank you. Record. Okay, so dear Michael, thank you for giving a talk and coming online at least to this conference. Okay, thank you very much.
Okay, Paul, can you hear me well, or should I tune my microphone louder or quieter?
I think it's really good now. I think really well.
It's okay. Okay. Well, welcome everybody to my talk. First of all, I have to apologize for not being in Cergy, but I felt that it was too risky to travel from one Corona hotspot to another. In particular, we have elections in Germany in 2 weeks, and all politicians hesitate to decide for strong measures against the pandemic. And so the numbers of infected people increased in Germany. And finally, I decided to stay at home at a safe place. So I hope you can understand this. But I hope that at least after the elections in our country, that everything gets better with the pandemic and that we maybe can meet in person in near future again. I very hope that we can reach such a state. Okay, so my talk will be on Bootstrap for integer valued Gauge processes. Wait. Okay, now it works. So here's an outline of my talk. First of all, I will introduce such classes of processes. Then I will briefly discuss a few properties of these processes and introduce a very simple method of bootstrapping these processes. And finally, I will conclude. So you will see that none of the results that I present today will be terribly surprising. My talk is more intended to be a methodological one. I will present a simple method based on coupling ideas, which makes simple proofs of all the results possible. So is there a problem? Wait.
Sorry. Sorry, I didn't catch.
Oh, okay. Does it work now?
No, we are still on the same slide.
Wait, please. What is wrong here? Paul, can you see my slide?
Yes, but we are just at the presentation plan now. That's okay?
Yeah. This is what was intended. Okay, and you can still hear me.
You can put it on the full screen thing, so we don't need to see the side of the red.
How can I do this?
That's
Wait.
Presentation full screen or something.
Is it now a bit
better? It doesn't matter. We see very well. Don't worry. That's it.
Okay. Anyway, on the left margin, there is still something which is not necessary, but I hope now you can see everything quite well. Okay, here's an outline of my presentation. And so as I promised, I will talk about integer valued Gauge processes. So where does the name integer valued Gauge comes from? I think that everybody knows what classical Gauge processes are. In the case of classical Gauge processes, it is assumed that one observes a random variable xt, which has this structure, and the epsilon t are random variables which are centered and have variance 1. And Gauge means in particular conditional heteroscedasticity. That means the conditional variance sigma t squared depends on lagged values of the x and the sigma process. This is a classical gauge model. And here you see the variance of xt, not xt squared, the variance of xt given the past has just this structure. So in the case of integer valued random variables, there's a close counterpart to this classical gauge model. In most cases, this is the most popular assumption. In most cases, it is assumed that the conditional distribution of an observed random variable xt of such a count variable is a Poisson distribution, and the intensity of this Poisson distribution is itself random and has a structure similar to the structure seen in the classical gauge model. So in this case, in this case, it turns out that the conditional variance of xt given the past, this is in case of a Poisson distribution, equal to the conditional expectation of xt. This has a similar structure as in the classical gauge model, and therefore processes with this structure are called integer valued gauge processes. Okay. So in my talk, I will use a slightly more general framework. As before, it is assumed that xt given the past follows a Poisson distribution, but for this intensity at time t, we also allow for nonlinear functions here. And theta 0, this is the true parameter, and capital theta is the complete parameter space. Okay, so the most important condition will be that this function f theta 0, the intensity function, has a certain contraction property, namely this one. It is assumed that there exist non-negative constants, and the sum of these constants is assumed to be strictly less than 1, such that the difference of this function at this point and at that point can be estimated in this way. So this is some sort of contractive condition, and you will see later on that under this condition we can easily derive properties of such an integer valued gauge process, and this will also be the basis for the consistency of an appropriate bootstrap method. Okay, now I turn to some simple properties of such an integer valued gauge process. For that, I put everything in the context of a Markov process. So the process consisting only on xt and lambda t is not a Markov process, but if we put enough of these random variables in such a vector, then we get a Markov process of order 1, and the state space of this process is, of course, this one. Okay. We will show in the following that the corresponding Markov kernel is contractive, and this will provide all the results that I intend to present today. So implications of this contractivity are that the vector valued process, this Z process, has a unique stationary distribution, and moreover, for the count process, we are able to show that this process is absolutely regular or beta mixing with coefficients decaying at an exponential rate. So everything is will be based on certain coupling ideas. And in order to describe how this coupling works, I have to introduce a metric on the state space. Here we have two members of this state space, and we measure the difference between these two members in this way. I come to the coefficients gamma I and delta j in a moment. So here, this is the first proposition, namely, in some sense, the Markov kernel of the Z process is contractive. So we suppose that the contraction condition on the intensity function is fulfilled. This is condition number one. Then it is possible to choose these constants here, gamma I and delta j, in an appropriate way, such that there exists some kappa strictly less than 1. And we can now define random variables Z and Z prime. Z has this distribution. This is a conditional distribution of CT, given that CT minus 1 equals Z, and Z prime follows that distribution. This is a conditional distribution of CT, given CT minus 1 equals small c prime. Okay, we can define random variables C and C prime in such a way that the expected difference between C and C prime is less than or equal to this constant kappa, which was strictly less than 1, times the distance of C and C prime. So, and this is some sort of contraction, since kappa is strictly less than 1. So the proof of this proposition is really very simple. So suppose that we have two members of our state space, Z and Z prime. And how can we construct corresponding random variables, capital C and capital C prime? So most components of these random variables, capital C and capital C prime, derive from small c and small c prime. We only have to define this and that component and this and that component. So the definition of lambda and lambda prime has, of course, follow the model equation. We have only one possible choice, namely this one and that one. This is quite clear. Otherwise, the model equation would be violated. By the way, here we see again some sort of contraction, namely the difference of lambda and lambda prime can be estimated in this way. Okay. And what about x and x prime? In order to generate x and x prime, we use one and the same Poisson process with unit intensity and just define x as the Poisson process at time lambda and x prime as the Poisson process at time lambda prime. So this gives quite a good coupling of corresponding random variables. Oops. And I must make it smaller. Okay. And it turns out that we can find constants gamma 1 up to gamma p, delta 1 up to delta q, such that this inequality here is really fulfilled. Okay. So in order to prove stationarity of this process, we have to represent this contraction property in a slightly different way. So far, we have here some sort of contraction property for the Markov kernel. Okay. But we also have to formulate a contraction property on the level of distributions. So in order to measure the difference between two distributions, Q and Q prime, we use the so-called Kantorowicz or Wasserstein L1 distance. And this distance is defined in the following way. We take appropriate random variables C following Q and C prime following Q prime, consider the difference of these two random variables and take the expectation. And then we optimize this by taking the infimum. The infimum over all random variables C and C prime such that their marginal distributions are Q and Q prime respectively. And by an optimal coupling of C and C prime, we actually obtain the corresponding infimum here. Okay, we take this distance between distributions. Once again, a reminder, PZ is a Markov kernel of the Z process. And here, this is our contraction result on the level of distributions. Again, we assume that our condition 1, this was the contraction condition for the intensity function. We suppose that this condition is fulfilled. Then we obtain for arbitrary distributions here that the Kantorowicz distance after one step is less than or equal to kappa. Kappa is strictly less than 1 times the distance between Q and Q prime. That means, in other words, the mapping which maps Q to Q and BZ, this is a contractive mapping. Okay. The proof here, or again, maybe you cannot see this. The proof is a direct consequence of the other contraction result. Okay, so now stationarity of the Z process will be a simple corollary of this result. Again, we suppose that condition 1 is fulfilled. Then it's quite clear that the C process has a unique stationary distribution. This is a proof. We know this was our previous result, that this mapping, which maps Q to Q and PZ, is contractive. The space of these distributions, which have here finite moments, is complete. And it simply follows from the Banach fixed point theorem that the corresponding Markov kernel admits a unique fixed point Q0, and this fixed point Q0 is the unique stationary distribution of this process. Mixing properties. Again, under condition 1, we can show that the count process is absolutely regular or beta mixing, and that the corresponding mixing coefficients decay at such an exponential rate. Here's a sketch of the proof. This is a formal definition of the mixing coefficients. Namely, we have to consider here the conditional distribution of the process starting at time n, given the process up to time 0. We have to compare this conditional distribution with the unconditional one. This is here the supremum provides the total variation distance. And finally, we take this expectation. This is a formal definition of a beta mixing coefficient. So since the C process is more informative than the X process, this is a simple upper estimate, but the C process is a Markov process, and therefore we obtain this. So now let's assume that we have two versions of this C process, which are started independently at time 0. Then we can estimate the right-hand side of the previous equation, this one, in this way. Okay, so this supremum can be upper estimated by the probability that there will be any difference between the xn tildes and the corresponding xn tilde primes. Okay. So, and this is how we get our upper estimate. Here we have to sum up these probabilities. We can estimate this in this way. So, and now we use our convergence result. These expectations converge at an exponential rate when we take a good coupling, namely the coupling that I explained before. And this finally leads to a rate of convergence of the mixing coefficients, which is such an exponential one. Maybe this picture here on the next slide explains what's going on. I simulated two versions of an in-gauge 1-1 process. So the left picture shows what happens if these two versions are really independent. Then you see here these solid lines are the corresponding intensity processes, the blue line for the red line for the first version and the blue line for the second version of the intensity process. And the points here, the small circles, show the corresponding count variables. So, and this is, there's really no dependence between these two versions, as can be seen from the left picture. And on the right picture, you see what's going on when we couple these two processes. Here at time 0, these two processes are started independently. And because of this contraction property, these two intensity processes get closer and closer. They don't coalesce, but they get closer and closer. But on the other hand, for the count variables, we see that here at some places, there's only one circle. That means at here, these two count variables are already equal. So here again, we have a small difference between these count variables. But finally, the count processes completely coalesce after some time. And this proves finally the mixing property of the count process. At this point, I have to mention that the joint process consisting of the count variables and on the intensity variables, this process is not mixing in general. There's a simple counter example which shows that mixing is not true in the general case. Okay, so bootstrap. So suppose that we observe realization small x1 up to small xn of our in-gauge process. For example, for the construction of confidence intervals or for setting critical values for hypothesis tests, it is required that we know at least some of the properties of the underlying process. So, and the bootstrap offers a method to get some knowledge about these properties. Bootstrap means that given our original sample, we construct an artificial process, which I denote by xt star. And we hope that this artificial process mimics the behavior of the original process. So in our case, we have a parametric model, namely xt as a conditional distribution, which is a Poisson distribution. And for this lambda t process, we actually have such a parametric model. This intensity function f only depends on this parameter theta 0. We assume that theta 0 is estimated by an appropriate estimator. For example, in this case, we can use conditional maximum likelihood. And now we can construct our bootstrap process. We choose any pre-sample values, and then we act iteratively. Suppose that the bootstrap process up to time t-1 is already constructed. Then the bootstrap version of the intensity at time t is obtained just by using the model equation. Okay, this time, of course, with the estimated parameter, because of course theta 0 is unknown, and xt prime is generated according to a Poisson distribution with this intensity. Okay, and now we, as usual, we hope for the best. We hope that the distribution of this artificial process approximates the distribution of our original process in an appropriate way. So the dominating approach in the literature is that we have some statistic of interest in mind, which I denote by Sn. For example, the normalized sample mean here. And for some reason, knowledge of the distribution of this statistic under p theta 0 is required. Okay. Then we construct a bootstrap counterpart of this statistic. And in most cases, it is proved in a more direct way that this artificial distribution, the distribution of our bootstrap statistic, of course, given the original sample, that this distribution is close to the desired one. Here, D is an appropriate metric, and this is a standard way of proving bootstrap consistency. Here, I would like to present a different approach, namely an approach which is again based on coupling ideas. Namely, we have two processes: the original process, the ZD process, and the bootstrap version, ZT prime star process. So, and our approach is to construct on an appropriate probability space versions of these processes such that the difference between the original variables and the bootstrap variables is small in an appropriate sense. And having such a general result, then the consistency of the bootstrap approach follows immediately for different types of statistics. This is the important advantage of this different approach here. Okay, here are some technical conditions. Of course, we need again, or we use again, a contraction condition for the intensity function. This time, of course, we have to assume this condition in the neighborhood of the true value θ0, because we have to estimate this parameter, and therefore we need this condition in a neighborhood of θ0. The second condition is that we estimate that the unknown parameter θ0 in a consistent way. This can be achieved, for example, by conditional maximum likelihood. And finally, we need a smoothness condition, which is written down here. Okay, so under these conditions, it is possible to show that there exists a coupling of the original and the bootstrap process such that here the difference between these two processes measured, of course, in this metric here is in some sense small. Here we obtain as a factor the difference between θn hat and θ0, but our assumption was that θn hat is a consistent estimator. That means as n tends to infinity, this factor here tends to 0 times something which decays to 0 as t tends to infinity. Here, this is the effect of different starting values of these two processes. Okay, the proof is again quite simple. We begin our proof with the initial values for these two processes, and then again we define lambda t tilde according to our model equation, lambda t tilde prime also according to the model equation. Here's a typo. This θ0 must be θn hat, of course, because we don't know θ0 and we have to estimate it. And again, in order to define xt tilde and xt prime tilde, we use one and the same Poisson process, and this guarantees that the difference between xt tilde and xt time tilde is not too large. Okay, this is the basic idea. And then based on these on this coupling result based on theorem 1, we can show that also the coupled process here, this is one version of the original process, this is one version of the bootstrap process. This coupled process has a unique stationary distribution, and the coupled version of the count processes is absolutely regular. So the proof is more or less as before. Now this time we consider two versions of this coupled process, and we just use this result, which was I have described already. Okay, what are consequences of this general bootstrap result? One consequence is that bootstrap works well, for example, for the sample mean. This is a simplest example, as n is here the normalized sample mean. Under our conditions, this normalized sample mean converges to a normally distributed random variable. The bootstrap counterpart is this one, and based on this, mainly based on this coupling result and also on the absolute regularity of the coupled process. Based on these two results, we can easily show that the squared deviation of these two processes, these two random variables, converges to 0 as n tends to infinity. On the other hand, as n has a non-degenerate limit distribution as shown here, and these two results together imply that Bootstrap works. So we can also derive consistency of the Bootstrap for other types of statistics, for example, generalized means, autocovariances, or even degenerate from Mises and U statistics. The ingredients of a consistency proof are again the same. We use this coupling result for the two Bootstrap process and the original process, and use in addition the mixing property of the coupled count process. And having this, the proof of the Bootstrap consistency for these types of statistics is really not difficult. Here's a short summary of my talk. My talk was or seems to be on Poisson in-gauge processes. I decided here for nonlinear versions of such processes. I have shown that a contraction condition on the intensity function f theta implies a contraction property of the Markov kernel, and also on the level of distributions we have a contraction. And an implication is that these coupling results allow us to get really simple proofs of stationarity, of absolute regularity, and also of the consistency of the Bootstrap, really for different types of statistics. So the results are already published. There appeared a paper in Statistica Neerlandica in this year. For some of you who are interested in details, you can find all the details in this paper. So thank you very much for your attention. I am now at the end of my talk.
Thank you very much, Michael. So, are there questions? Yes, please. I'm sorry. I have to look for the microphone. He should be.
Hello, Michael.
Hi.
Thanks for the talk. I was wondering, what is exactly the distance d that you use for the consistency of the Bootstrap distribution? Is it the same kind of Wasserstein matrix that you use for contraction, or it is completely different?
Okay. Yes. Here you see.
It's not on this slide. It was written d.
This is yes. This is exactly the same metric that I have used before.
Okay, thank you.
And yes, and this metric was defined in the following way. We take the components of these two vectors, consider the differences of these components, weight them by gamma I and delta j, and sum up. Yes.
Okay.
So, yes.
I was wondering about the contraction condition. Is it possible to get the same result if you start with beta mixing condition instead of the contraction, or is it? Do you have to? Do you really have to use the contraction condition?
I'm afraid that the answer is negative. I mean, everything in my talk was based on, say, some sort of physical coupling of two versions of the process. And this physical coupling was successful because of this contraction condition. So I have to go maybe at the very beginning of my talk. Yes. I mean, yeah. I mean, your question is what happens if we replace this condition number 1 by some sort of mixing condition, right?
Yeah, right.
I mean, this is a completely different game. So at least with the methods that I have presented today, it's impossible to go the same way as I have gone with my work, because really everything was based on, say, physical coupling of the corresponding random variables. So the answer is no.
Okay, thank you.
So thank you, Michael, and thank you to everyone. We thought it was a good idea to. So I'm sorry, I didn't applause. Sorry. So I will just stop a bit the record because where is that story? Okay. So thank you for even coming to Sergi, which is a really challenging thing. And so we wait. I'm sorry. So I put your slides and then. Yeah. So Catherine, yeah.
Okay. Thank you very much. Ça marche?
Oui.
Ça marche.
This one also works.
Ok. On va pas faire des trucs trop. Oh yes, thank you, Paul, for the invitation. Thank you, everybody, for being there this morning. Difficult this morning. So I'm going to give a talk about local convexual. How can we use a small convexual to estimate density and its level set? Okay, in this talk, there will be statistics, obviously. There will be no dependence. Okay, but it's a method which is clearly applicable to ecology problem. Since I will talk about a paper, not in math from the beginning, the paper from Yates and Wilmer from 2004. It is very popular. It has 475 citations, which is, I think, I never have on all my papers on all my life this number of citations, and it's not mathematical at all. And they propose a method to estimate home range and core area of animals, and they just describe an algorithm. And they say, okay, we observe points in RD. Let's call them XE, not original at all. And for all let's compute the convexil of not well written at all. The convexual of the k nearest neighbor of the point xi. We no, we plot the convexual. We compute the convexual and we compute its volume. we sort everything by decreasing volume, and we plot the little convexual with an increasing level of gray. Okay, that's what they say. So little graphic to try to illustrate that. I take a point. I take its 12 nearest neighbor. I compute the convexual. I do the same with this point and with every point, by the way. And then I compute the volume. This volume is larger than this one. So I plot this convexual first in a light gray, and this one is the smallest. I fill it with black. I do that. So it works very well. Maybe I can make something very quick. Check. Okay. And that gives such a type of graphic. This is Panthers locations. I don't remember where. So it works well. Yeah. What is that? How do they do that? What? If I want to translate their work into mathematics, what do? They estimate the density with a k-nearest neighbor formula, where you take the number of neighbors, you divide by n, and instead of dividing by the volume of the ball, you divide by the volume of your little convexual. The point is, with their level of gray, what they do exactly, they exactly estimate the density. By the way, we were telling it because it's not my question, by the maximum for all I, so that x is in the small convexual of this division. And they estimate the level set as the set of points where the density is larger than the level. Okay, so that's more classic. Okay, as I told you at the beginning, this method is very, very popular. And I wanted with Ricardo Freiman to study it mathematically, to see if it's consistent, not consistent, where there might be problems, and can we correct the problems and improve the things to have a better method. Because there is problem. And the first problem that maybe it's quite easy to see is that, okay, let's start by the problem. The problem is that we clearly overestimate the density. We overestimate it twice. Once because the usual nearest neighbor density estimation, here you divide by the volume of the ball of the radius, and here you divide by the volume of the convexual of the sample points that belong to this ball. And so this volume is clearly lower than the volume of the ball. And so you divide by something too small, so you overestimate, and moreover, you take this max, so you do huge overestimation. That's the non-good point. And the very good point is that when you have densities supported by a compact and with gaps, the density, what we like in set estimation is that we have densities that are bounded below by a positive constant on the support. Yeah, the density fails when you go very, very fastly to zero when we go out of the support. When you want to estimate the density on a boundary point, you have a boundary effect in usual density estimation methods. And with that, we may correct that because we mostly fit with a better volume. Okay, so what we want to do is okay, try to correct this bias and take the advantage of having a globally good behavior in particularly close to the boundary, which is not the case with other density estimation methods. So for thinking simplicity, we always start doing, okay, k-nearest neighbor are very good, but we start with fixed radius that decrease to 0, and say, always say we will go to the k-nearest neighbors after, and after we always forget to do that. But okay, let's do that in not a nearest neighbor context, but with fixed radius. We need first to put some hypotheses. The hypotheses we make in this kind of domain are always more or less the same. Yeah, it's a bit restrictive. We have better results, but let's start with this one. We always have IID sample. Okay, sorry for the depth. We suppose that we have a density which is bounded below by a positive constant on the support S. And we will also suppose that the density is of class C2 on S later. But on S, it's bounded below by a positive constant. Our support, we want it to be regular enough, the boundary to be regular enough. There is a popular condition, what we call the rolling ball condition, saying that which is a regularity condition, which is this one. I just put a picture here, which is better. At every boundary point, you can put inside ball, inside the support ball, that touch the boundary only at your point, and which is totally included in the support, and the same outside the support. And it's very nice condition. Mostly it says that the boundary is a C11 manifold. So one differential with a Lipschitz condition on the normal vector for more standard way to say things. But yeah, having such kind of conditions is nice for making proofs with no use of differential geometry and only Euclidean geometry. That's nice for that. You can do differential geometry without the differential. What is exactly our estimator? As I told before, we are going to work with small convection. So at each point with a radius Rn, we are going to look at the convection of the observations that are in the ball of center X and of radius Rn here. And we are going to estimate the support as the union of all these things. So that's the first work we did with my friend Olivier, long time ago now. If we do that, it's really nice. We have a lot of good properties. We know that the Hausdorff distance between the true support and the estimated support is of such order, which is a minimax order. We have convergence between the boundary of the support and the boundary of the estimation of the support with this order, which is also the minimax. And we even had a result saying that eventually, almost surely, we had homomorphism between the support and estimation and the boundary and its estimation. I got here the result of the estimator on seism. The yellow is the support, the estimation of the support of the location of the seism. I don't remember a huge lapse of time. The red part is more than 6 on the Richter scale seism on the same time. So you can draw maps. What about the density? So we spent some time between the study of the support estimator, between them and the estimation of the density and then the level set, which are also nice, because we, by the way, for the study of the density of the level set, we use two recent works, one of Baldwin and Race from 2015 and another one from 2017. So time to get this result published and known, work with that. Well, we need time. So what is the density estimation? The density estimation is a bit more complex than the one used in the original paper in ecography by Getz and Vilma. What do we have? We have here, instead of the number of points in the ball of center X and of radius Rn, we have the number of points which are in the interior of the convection of the ball of center X of radius Rn. What we do in here, we divide by not the size of the sample, but the size of the sample minus the number of points that belong to the boundary of the convection. Yeah, it's the volume of the convection as in the original paper. And yeah, you need just to put in indicatrix just to avoid dividing by 0 or too small stuff. Yeah, just prevention. What about that? Okay, we take the same hypothesis and for the support, just add a regularity condition on the density. What about that? We have that our density estimation is as good as the kernel or nearest neighbor density estimator, which is minimax for all points that belong to the interior of the support, when the dimension is smaller than 7. We have an extra additional result, which is that the density estimator converges everywhere in the support, so included on the boundary of the support with a rate which is the square root of the rate inside. So we have that for the expected square of the error. We can derive rates of the same order up to a logarithm here for probability and deviation equality. And what we get is that, so if I take all the observation with exactly the same rates, we have that for all observation, our estimation doesn't differ too much for the true density. And having uniform result on observations allow us to estimate the level set of the density using exactly the same method than the one proposed for the support. So we have uniform in rate everywhere, and if I am far away from the boundary, I have better rates. I would like to show you a bit of the proof of that, just to convince you, so that you can see why there is this 7 here that appears, and why we can do. So first, let's get rid of very quickly of these terms. These terms are eventually almost surely 1 under our conditions. I don't want to spend a lot of time on that. It's very easy. For instance, this one, the number of points that belong to the convexure, to the boundary of the local convexure, is less than the number of points that belong to the ball of center X and radius Rn, and it's obviously something that is very, very negligible before n. So this way. This is a bit more difficult to prove, but in the domain it's very classical. You say here it's because you suppose, as usual, that n times Rn power d goes to infinity, so that you have enough points in each ball, so that when you take the convexure, we recover at least half of the ball. So take a equal 1 and 2, and it's okay. The more fun part, more beautiful part to concentrate on is this part, to see why appears these points that belong to the interior of the convexure, and here the points that belong to the boundary of the convexure. And it's, I think, very nice how it appears. It is due to this decomposition. Okay, I can decompose the difference between the estimated density and the true density as the sum of two terms, and the two terms goes to 0 for different reasons. First, let's see what is this epsilon1 term, and just look at this one. The number of points in the interior of the convexure minus what I call gamma tilde. Gamma tilde is what? It's the integral of the density, the unknown density, but the integral of the density on the convexure. Time on this one. Everything's go well because of this. What is the law of the number of points in the interior of the convexure, knowing the convexure? What is the law of this number? Conditionally to the fact that we know the convexure. So it's in the paper of Balin and Race, and they explain, I think, quite well, how we can condition by the knowledge of the convexure. It's possible to define that. So let's assume that I know the convexure. If I know the convexure, I know the points that are on the boundary of the convexure. My convexure is a polygon, and at all the corners, you have an observation. So I know exactly the location of this point. What is random again? It's n, the sample size, minus the number of points on the boundary. And the probability to be in the interior is exactly gamma tilde. And this only small remark make that do that we can do a very easy probabilistic calculus on epsilon1, and we have, for instance, that the expected value of epsilon1, the square of epsilon1, knowing the convexure, is less than that, and after you just have to derive very easy stuff. You wouldn't think everything is okay, and you have here something which is which is on 1 on n times Rnd at the denominator. If you want probabilistic goods, you just have to use Bennett inequalities. It's the same. Okay, so that's for this term. And now let's have a look on this one. And what happens? I can read, yes, we recall that tilde gamma is the integral of the density on the convexure. And so I want to first, if I look at the difference between the integral of the density and the integral of the constant density fx, because of regularity condition on f, it's clearly something which is big tau of Rn. And if I'm a bit more, if I do a bit more, I can just say, okay, this difference, I want this difference. I introduce the integral on the ball, and then I remove the part which is in the ball, but not on the convex shell. And what happens if I am far enough from the boundary? This integral is classically big tau of R2, as in classical calculus in density estimation. You do a Taylor expansion, and it's okay. What about the second term? The second term, yeah, the integral of the difference between the density and the constant on the ball without the convex shell. It has been very intensively studied by Victor Emmanuel Brunel in a preprint of 2017. He gives all the asymptotics of that in a very large class or very large class of condition, and we are under its condition. What happens? It happens something. This term can be neglected before with respect to the overall term, only for small dimension. It's this term, because of this term, that the if d is less or equal to 7 appears in my theorems. And by the way, I don't see I have dimension not very realistic maps. If we want to estimate the level set, we have to impose conditions on the level set, and these conditions are very very classical. We want to be able to see things. We want the level set to be regular enough to have the rolling ball condition that I presented to you at the beginning. We want it to be not only at the level t we want it to estimate, but in a small neighborhood of t. So for all t prime close enough to t, we have the same smoothness condition on all the level set. We need that, and we also need that our level set are regular, which is the most of these ones between two level set. The level set we wanted to estimate and the level set with a closed level is of order the distance between t and t prime. That morally means that you don't have a flat part on the density. In other words, the gradient of the density is lower bounded at t. Well, it's exactly that. And if you do that and take the same radius and for the density estimation and estimate the level set exactly as we propose the estimation of the support, which is I take the union of the convex shell of the observation points where the density is greater than t. If I do that, I will have very good results in level set estimations. And what I want to say is not exactly the same that what was in the original paper of Getz and Wilmer. What they do, the same thing, they got the union on the same set, but not of the convex shell of the points that are of high density, but of the convex shell of all the points. And here we have something which is included in that and which is more precise. We have exactly the same kind of convergence rate than then for the density, we say, okay, if I have a regular level set, we have a convergence rate, which is of this order. And if I have a regular level set that is far enough from the density, I have a level distance between the two level sets, which is of this order. And I apologize, there is an additional logarithm term that I need to put. This is the kind of maps. Here you can see the maps on the pointer, which is with the original algorithm. And here you can see the map of the pointers drawn with the improvement, because I think it's improvement on the algorithm we propose. What you can see is that okay, you clearly have the inclusions. Here it's a bit more regular. Looks like that. So you can go plots like that. What do we want to do after a lot of things? What happens is that if I work in other distance, we have the rates proposed even for level set that meet the boundary. But if we want to work with the measure of the distance, the symmetric difference, we must have something much smaller, which, okay, just detail, but it can be interesting. If I want to estimate the volume of the level set, we can have better results. It's what we are currently doing now. Okay, the point that we want to develop is to work with the nearest neighbors instead of the fixed radius, because of a lot of things. Because working with the nearest neighbor prevent us from the indicator stuff, because we are sure not to divide by 0, and that's good. The problem is that okay, over good things, it's more adaptive and to difference. The bad point is you lose a lot of robustness because you take everybody. And we would like to go to just make small modification in a way that we can use such an estimator to estimate density and manifold with boundary. So here are all the paper on in which there are key points used in the proofs. Okay, that's all.
So thank you. So are there questions?
I was wondering, how do you compute empirically the good value for the radius Rn, or the number of the neighbor k? Because I see you suggest a value, but you cannot see which cannot be estimated in.
I don't suggest values. I give asymptotics as I say, okay, you clearly need to have a Rn which is of order, I don't remember this one.
Yeah.
Exactly the same that for density estimations. I don't select the parameters. It's always it's a difficult part. It's clearly the difficult part. And I must admit that I try always in my papers to have a part where I say, okay, that's a good value, but yeah, it's just too much in progress to have that. It's a good point. You select it exactly as for the density, I say. If you have a good one for the nearest neighbor,
Yeah.
Okay, yeah, you take the same, it will work. It's of same order. You just you clearly have just up to a constant your rates are the same, and the one that comes from the one that comes from. By the way, you exactly have the rates of the classical one without the convection, and you can neglect this term, which is the one that is not good for small dimension. So believe me, you have the same rates than for the classical one. Take the same.
So I don't know if there are no more questions. Maybe we thank again the speaker and we stop sharing. Yes. Okay, so thank you actually for coming, and wait, I have to do some manipulation to make it work. And so here we are, and I share the screen for you. So thank you very much, Adam, and I let you work.
Okay, thank you. I would like to thank you for invitation. I always like this specific atmosphere of conferences organized by you. It's I participated in several, and I like it very much. My talk will be about some work in progress. I mean the last things here will be in this is the work in progress. But before, I want to make some self-promotion. And this promotion is related to my function in Bernoulli Society. Some days ago, before coming here, I was in Lausanne, and in Lausanne, I've got a Bernoulli book. This is the symbol of presidency of Bernoulli Society. So we met. Here is Claudia Krippelberg, the previous president, and here it's me. I am currently the president of Bernoulli Society, so you can call me president from now on. Well, so of course this is a opportunity to show a photo of this kind, but of course there is something behind that because I'm in France. Of course, the audience is not hundreds of people, but perhaps some information can be passed to other people, namely that it's my impression that French probabilists and statisticians are underrepresented in Bernoulli society. This means that, for example, comparing to people, to countries as rich as France, Germany, Holland, Belgium, Scandinavia, there are many members from those countries, while from France it seems to be that it is of no interest for French people. That's too bad, because, and this is the reason for my presentation, to promote Bernoulli society, not membership in Bernoulli society, not in terms of profits you can get, because at the moment the profits are rather problematic, while because of importance of Bernoulli society to the world of probabilists and statisticians. We publish journals, and we know, of course, that it is a Bernoulli journals, relatively new one, and stochastic process and their applications. So it is, in a sense, we are are responsible for appointing the editorial boards and so on. So this is a kind of service to gain to the world's society of probabilities. Here, I would like to stress true open access journals, because at the moment they call open access journal. If you want to publish, you have to pay. Maybe for you it's not a problem, but a friend of mine, being on the desk in such a journal, got a message from a person from India, and he said whether it is possible to decrease the fee for that. So it's, in theory, it's open access journal. You can submit, you can get the paper accepted, but then to be published, you have to pay. Not very high amount, but for some people, this can be a problem. So these are true open access journals, you know, electronic journal of probability, electronic communications in probability, probability surveys, statistics surveys, and electronic journal of statistics. They are with IMS. This is some other factor also. What does it mean? They are, for example, accessible on Project Euclid service. It's not for free. It's not for free. So this means that all those things we are used to send papers, read papers. They are in fact supported by those two societies. In this case, IMS and Bernoulli Society as well. We have, of course, some publications for members. This is maybe not so interesting, although this is a kind of Bernoulli news. This is a kind of chronicle of Bernoulli, of events in the world. Some other journals I will not mention, but for example, this is interesting, serious, and also not used by not but French people. Only three books are published in this series every year, while it seems to be quite a good idea to have such a journal. We organize conferences every 4 years. Bernoulli IMS World Congress on Probability and Statistics. This is the proper contemporary name of that. In the past, it was only Bernoulli World Congress. First, let me remind you, it was in '86 in Tashkent, still in Soviet Union. The recent 10th World Congress was, of course, planned in Seoul. Due to pandemic, it was necessary to postpone it. And finally, it was online held in July. And this year, quite successful. Many participants, even financially successful. Unexpectedly, the fee was quite high. One has to say that with support and of Bernoulli and IMS, there was One World Symposium, some kind of replacement for Bernoulli Journal. Also, the information that the next World Congress will be in Europe, in Bochum, in 24. So closed. I mean, not so far. The other conferences here, numbers are important. Look. The first conference on stochastic processes, 1971. 41st SPA conference was in 2019 in Evanston. Next, 42nd will be in Wuhan. This was planned for this year, but the shift of the World Congress caused a shift to the next year. We'll see, of course, if it is possible to organize it in this time in physical world, but the number 42. Every researcher who lives, say, some years in the and travels and visits conferences knows that there are sometimes cycles of conferences rising, then falling down, disappearing. Here you have 42 42 conferences. This is due to the fact that Bernoulli Society does exist. Otherwise, this could be changed and so on. This is some kind of continuity. The other conference of meaning, well, it's of similar meaning is European Meeting of Statisticians. First was in '62, before Bernoulli Society was established, but recently it was 32nd in Palermo, and the next year there will be in Moscow. You are invited. It's not so, again, it's not so distant in a sense, despite maybe in a sense not exactly the same exotic as it used to be, but of course it's Russia is not completely the member of international society. Okay, at the moment. What is really successful are Bernoulli IMS Young Researcher meetings. This is also okay. So this is the last thing. We have prizes. Once again, Bernoulli Society New Researcher Award. It's quite successful. Many applications. Of course, focused. Some center dominate. No, but this is because there are no candidates from other countries. There are some other prizes in 21st. Some new prizes. We have a Bernoulli Society, a new award, Bernoulli Society Royal Statistical Society. So this is a joint initiative of two societies. David G. Kendall, the name of the first president of Bernoulli Society, Award for Young Researchers, and the first winner is here, and also newly established Willem van Zwet Medal for Special Service to the Bernoulli Society. Maria Eulalia Vares obtained this for the first time during the World Congress. So what is the conclusion of these 10 minutes? I mean, now we are in the schedule, I guess. What is the conclusion? Simple. If you want to support the international society, I mean, the international probabilists or statisticians, you should belong to some statistical societies because they provide continuity for our tradition, for the conferences, for awards, for publications that are very important for all of us.
So, sorry, may I just add something concerning the Young Researcher Award? I think that we heard yesterday the talk by Nakuato, which was a member of the
earlier. Yes. So okay, this is of course the way of selecting potential leaders. Yeah, because most people, usually such people are more active than the others. So this is important for us. Okay, now it's time to come back to the topic. I would like to tell you a story about the phantom distribution functions. This is a topic I like, but it is surely not commonly known. Therefore, I will give a long introduction. I guess I can convince you that this kind of thinking about results for stochastic extremes can be useful. Let us start with classics. We are, of course, everybody, maybe not everybody, but it is very classical result and for a long time, that if we consider maxima of IID sequence, then due to works already, I guess, approaching 100 years, Tippett and Fisher, we have a situation such that if we investigate maxima, partial maxima, suitable centered and normalized, then we have a convergence in distribution to a non-degenerate limit distribution, of course, under some conditions. And first The idea is that there are three classes of non-degenerate limits: pressure, Gamble, Weibull. Now, this is a classical idea, and also due to works of Gniedenko and Dehaene mainly, we can precisely describe to give precisely necessary and sufficient conditions for this given distribution function, marginal distribution function f, to belong to the domain of attraction of some extreme value distribution. So this is the, in a sense, a complete analogy to the theory of sums of random variables. And this theory, of course, is not really well known. There is a relatively new book, Extreme Value Theory by Dehaene and Pereira, but the other, older, by Leadbetter, Lindgren, and Ruthen, still can be a source of good results, because there are computations, classic computations from the golden era of this theory. It was in 70s where many results for dependent random variables were done, stochastic processes, and this book was devoted exactly to. It contains a summary of those results and can be very instructive, still can be very instructive. So we have classic theory, nothing to be done. But on this perfect image, there is a blemish. Consider such a distribution function with tail of this type. You can check this is this here. There is a convergence to zero. It's a continuous distribution function. Suppose we try to compute the limit for maxima from such a, for our purposes, of course, chosen, but distribution function with super heavy tail. Because of this heaviness, it does not belong to the domain of attraction of any extremal distribution. So the previous theory does not apply to such random variables. But if we consider a sequence of levels, then the probability will be non-zero. Yeah? So there will be some limit. Moreover, for each gamma, we can find a sequence Vn of gamma of levels such that there will be a limit to gamma. So we can calculate approximate quantiles, for example. It is important, and of course this is not our observation, it was observed already in 70s by O'Brien, that this existence of Vn gamma for each gamma is implied by existence of at least one such Vn. It is not surprised. This fact is not surprised. It is not the special property of this fact. In fact, the asymptotics of maxima is by these sequences is completely determined by a single sequence of levels. Namely, in particular, it follows from this sentence that I will give a precise sense to that if we try to calculate the classic convergence, and if we are able to prove such a convergence for some x0 such that the limit is non-degenerate, is neither 0 nor 1, neither, okay. So then it follows that for all other x, we have already this kind of convergence. So this means there is this superfluous information. Of course, this is important to know that this sequence Vn can be of this form, a linear form. So this is additional information. But from the point of limit, it's clear that we don't need, we should, because the asymptotic behavior of those probabilities is determined by one sequence of levels. There is no there is no information, essential information in the other in the other sequences. Yeah. So in a sense, the classic theory is too similar to the theory of songs. That was exactly searching for a complete analog of theory, limit theory for science. Now it's time to make those statements precise, and this will lead to some property that it's funny that the results I will present in a moment were published only in 2015, while the theory was developed for at least 90 years earlier. Of course, I do not say that the theory replaces the whole existing theory, but simple such statements should be available earlier. We say that G is regular in the sense of O'Brien if in its right end of the distribution it's continuous, so there is no atom in the right end, and jumps do not dominate the tail. Jumps do not dominate the tail. So jumps are allowed, but they do not dominate the tail. We have the same. This notion, of course, we call it regular. It's our name, but of course the computation was done. Observation, in fact, was done in 70s by O'Brien. Regularity, in fact, this statement, those two conditions, is equivalent to the existence of a number gamma, such that we have this convergence, and in fact, for existence of for each gamma of such sequence V and gamma. So this is exactly the thing that we appointed. We found in our example with super heavy tail. The idea is that not all, of course, distribution functions belong to are regular in this sense. For example, Poisson distribution or geometric distribution, they do not have distribution functions which are regular in this sense. But of course, every continuous distribution function is regular because we can take as Vn simple. We can find such Vn for each gamma easily for continuous distribution functions. And here comes the statement. Suppose we have a regular distribution function and consider any other distribution function. This is the result from paper by Paul, myself, and Gabriel Lang from Extremes in 2015. We have the following statements equivalent, that the behavior of maxima of random variable with this marginal distribution function G is the same as if the marginal distribution is H. This is equivalence of that. This fact is equivalent to the information that we can find for given the same limit. We can find a sequence that those powers behave the same way. Not exactly, they need not be equal, but they have the same limit. So this is related to our previous properties and says, in fact, already those two facts say the asymptotics of G of maxima for independent random variables is fully determined by a single sequence, yeah, because those two facts are equivalent. And one final statement that this function H must be regular to have such a thing, and its tail is equivalent to the tail of G. We have equivalence of tails. Right ends must agree, and we have equivalence to tails. So this is a complete characterization that I think should be provided in those textbook, classic textbook, as one of first sections, because this is the view into the structure of maxima of IID sequences. In particular, once again, I would stress this says the asymptotic of maximum of IID sequences is determined by the limit, non-degenerate limit along one particular sequence of levels. Now we can go to the notion of phantom distribution function. So far, it was some analysis of the classical independent case. This notion of a phantom distribution function, it's only for maxima, but we use this terminology, was introduced by O'Brien in '87. He, using renewal structure of Markov sequences, Markov chains, was able to define such a phantom distribution function by given formula, in a sense. But after extracting, it seems that this idea is much more pliable. That means we can find many more examples than only Markov chains. Suppose we are given a stationary process with partial maxima, stationarity without any additional assumptions, marginal distribution function f for future purposes, then we say that xj admits a phantom distribution function g if we have if the asymptotics of maxima for this stationary sequence is described by the function, by this phantom distribution function g, that's powers of g. So of course, if mn is a sequence of independent random variables, that we can take as gf, but in general, of course, no. What is obvious from this definition is that g is not uniquely determined, and if we take any other h distribution function, then we can again describe, if this holds, then of course this relation holds with h as well. So the final statement is that it follows that the phantom distribution function is determined uniquely, but up to equivalence of right tails from the previous result. Why to deal with phantom distribution function? Again, it's interesting, some kind of multiplicative structure. But here we see that this term is determined by convergence along one sequence only. Yeah, by such, the asymptotics of this term is described by this fact. So this, because of this equivalence, we see that there is also asymptotics of those maxima for stationary sequences are completely determined by a single sequence satisfying such things. So we have a basic statement. If a stationary process admits a regular phantom distribution function or continuous, this is equivalent, then the asymptotics of maxima is completely determined by a single sequence of levels of this type. So if it admits the asymptotics, to know the complete asymptotics, we need only to check this one relation. And for example, if gamma is one half and the distribution function f is continuous, then we can take the median of maxima, for example. It's obvious that such a sequence does exist. So of course we have this sequence at some situations for free in a fact, and of course it's necessary to check some other conditions, but the conditions are not demanding. In the same paper quoted already, we have a complete characterization, and this is a bit insightful. It's not that we change that's the same formulation in some languages. There are three formulations, equivalent formulations. If we have a stationary function, then we have xj admits a continuous phantom distribution function. This is what of interest for us. one can find a number gamma such that we have this, we know this is natural. And for each t, we have the following condition satisfied. This is the B for breaking with time horizon t, because we see that t is here. If we, for each t, we can break asymptotically those probabilities. This reminds, in a sense, independence or asymptotic independence, but it is not. It is not. The warning says one can. The third formulation is that one can, and this is sometimes most useful, one can find a number and a non-decreasing sequence Vn such that if we take partial maxima, we consider them as a process in T. Yeah, this is the floor of the number nt. Then we have convergence to gamma to T on some, this enough on some rationals or some dense, other dense sets of reals. So we have three different formulations. This is the something what is deserved. Here is how to say, it's a general statement, and here practical statement. So it works. I mean, this machinery works. In fact, many stationary sequences admit a phantom distribution function. For example, any alpha mixing stationary sequence is continuous marginal distribution admits a phantom distribution function. So there exist non-ergodic stationary sequences admitting phantom function. This means that the condition we previously introduced, it suggests some kind of asymptotic independence, but there is no asymptotic independence for in the original sequence. Only on right tails is, because we can find non-ergodic stationary sequences. So with some structure, internal structure, but still they have a phantom distribution function. There are, and this is also interesting, there are stationary sequences that admit a non-trivial continuous function distribution function with the property that if f to n, this is the maxima of independent random variables with this distribution function f, the same as our original sequence. Yeah, if the limit is non-trivial, then our in fact our maxima go to 1 with this sequence. Here I should use Vn, I guess it would be. This is so-called property, which is the extremal index 0, but it says that maxima of our stationary sequence increase, they increase slower than the corresponding maxima of independent sequence with the same marginals. Some standard examples: if the covariance function of a standard stationary Gaussian sequence satisfies the Berman condition, Rn n to 0, then phi of x, the normal distribution function, standard normal, is a phantom distribution function for our sequence. But if this Berman condition is violated in the form, then this sequence does not admit any phantom distribution function. So this means it is known that in this case there is a limit distribution for maxima of this Gaussian sequence, but it is not it is in fact a mixture of some Gaussians and so on. This means that in this case, this maxima of this stationary sequence cannot be described by a single sequence of levels. Yeah, because you need then the whole family of levels. So let me finish. This is the theoretical part. There are some constructions of estimators which, based on this philosophy, they are stable, but the pandemic slowed down the works, and they are not ready for publication yet. It is necessary to smooth something and so on. But it is very promisable, and one I can say it confirms that this can be the philosophy using a phantom distribution function, or this single level thinking brings good results in data analysis and in simulations. What is the situation related to more complicated structures like ZD? And our aim, I mentioned something on trees, but before we have some structure which is rich by itself, very regular. This is the lattice, yeah, over ZD. We have then a natural partial order, and we can of course consider a stationary random field. This is a d-dimensional stationary random field. That means a family of random variables indexed by this lattice. Single distribution function is f. We define partial maxima as the maxima over rectangles. Here we have the inequalities in this partial order. Of course, it's clear how to imagine this thing. Of course, people would like, and the referee of this paper that I will quote in a moment, liked much more situation general, that it is indexed by any subset. But of course, then let us study first this particular case, which is easier, much easier to see that the situation in case of random fields, as usual, is not obvious. We had this morning a lecture where Martingale central limit theorem, standard Martingale central limit theorem, was clearly, it was not easily transmittable to the language of random fields. Okay, we have so our problem is we have a maxima over rectangles, in fact, increasing, but of course not squares, rectangles, general thing. And we want to study the maxima, such maxima, from the point of view of existence of a phantom distribution function. So, well, again, motivated by independent case, if we have IID field, then of course here we have a simple f of x2 and star is the product of coordinates, yeah? Is the product of coordinates. So for independent field here we have 0 always, yeah? There exists the marginal distribution function. Therefore we adapt the general definition to random fields in this form, natural form. Only notational difficulties here are that we have a n bold, which is the d-dimensional vector, and the n star appears as the product of coordinates. So it's natural idea. Here it is reference to a paper by myself and my PhD, that time student Soya Kukiwa in Extremes 2019. We have, using this definition, we show that many stationary random fields admit the continuous phantom distribution function in this sense. For example, M-dependent, when we have the limit to dependence or function of IID random fields. Multidimensional moving averages. The idea is that we know what does it mean moving averages for time series. Multidimensional means that we make summation over some squares or infinite over the whole plane or space and so on. So multidimensional moving averages, then also moving maxima, similar with heavy tails. Yeah, Gaussian fields satisfying the corresponding Berman condition. It is possible to express it quite easily. Also, here one can mention a paper by Wu and Samorodnitsky. They considered random fields with so-called tail field. There were elements of regular variation of processes mentioned in Gennady Samorodnitsky talk. So there are examples of such random fields with phantom distribution function, continuous phantom distribution function in this strong sense. But it appears that it is too strong in a sense. It's natural generalization, but very strong. To be able to describe the situation, to provide a suitable counterexample, let me introduce a monotone curve. This is quite natural. It seems this is the sequence of points in the lattice, our ND lattice, and simple such that by coordinates, it is all coordinates are converging to infinity. We have a monotonicity in each coordinate, and we do not assume that this can stop somewhere. Moreover, we assume that the products of coordinates converge to one. It is important to have this property. So we can say that G is a phantom distribution function for this random field along such a monotone curve if we have a natural definition. This is the definition of previously introduced, but only around a curve. Yeah. Here we have a sequence of points. And we have observation once again, but it is not completely trivial observation. G is a phantom distribution function for Xn if and only G is a phantom distribution function for Xn along every monotone curve. And the continuity plays a role here along every monotone curve. So it's reducing, in a sense, reducing the general statement to geometric objects, I mean to monotone curves of this type. And we have a general result. A stationary random field admits a continuous phantom distribution function if the following conditions again is satisfied. Here we have a familiar condition. We need a convergence according to, but here is a field of levels. N is bold, so it is not a sequence, this is a field of levels. But this field of levels does not depend on the shape of the rectangle. It depends only on how many points this rectangle counts. So this is a strong requirement in a sense here. We say strongly monotone if the sequence depends, in fact, is a function of n star, not of n. And for every monotone curve, we have the condition, a version of this condition previously mentioned. And well, it looks discouraging, but we have a simple illustration in 2 dimensions. We have a rectangle. We have some point here P plus Q. So we can break this rectangle into 4 rectangles, and they have to be asymptotically independent in the sense that products of those rectangles must be, I mean, the maxima of those over this rectangle should be broken into product of 4 maxima, 4 in case 2, of course for 2 to the power d if the dimension is high. So we have quite intuitive version of this asymptotic property of breaking probabilities. Yeah, that's therefore we use this property. But one comment is relevant here. This is a theorem, bringing a complete solution, in a sense, to our thing. Suppose that f is continuous, and we define Vn as then of course the distribution of Mn is continuous for each n. We can just take Vn as a kind of quantile of order gamma. Then trivially we have convergence, and this field of level is monotone. It means if we take n bigger, so bigger rectangle, then clearly this field Vn is in proper relations. So it is monotone with gamma fixed, but there is no reason to expect it strongly monotone. It depends on particular point of the square, and it seems that the strong monotonicity is very strict, very requiring condition. It is satisfied for random fields which are in a sense very close to independent random fields. We have example exactly from the paper by Jakubowski, Rodionov, and Soja-Kukiewa. This was the previous theorem was also from this paper. This is published in Bernoulli 21, and we have a construction. We consider stationary random field with standard in a sense, but with a covariance function. These are elements of the random field. Yeah, so indexed by 2. Stationary, so we need only this to write down this covariance functions should be of the form, it's a product of I and j, where those two functions are characteristic functions. We assume that n1, eta 1 and eta 2 are symmetric around 0 and convex, so we can apply well-known Polias recipe to construct. Then we assume that for I and j large enough are like this covariance function is of this form. Clearly, the reason here for I and j large enough is that this has no sense for small I and j. Yeah, so we have to extend it using the Polia recipe to get such a function. And then it appears that for this stationary random field, the standard normal distribution is a phantom distribution functions for xij along the diagonal. But there is no phantom distribution function along such a monotone curve. So this means that there is no global phantom distribution function for this random field. One can check that from this form that if you look at the function R psi n, when psi n is exactly given here, then multiplied by log of n, it converges to a non-zero contrast. So this is the case where there is no for random variables, Gaussian random variable, Gaussian random sequences, there is no phantom distribution function. Yeah, and also in this case, one has to say that the covariance structure over rectangles of this shape is much more complicated than in the linear case. So all computations had to be performed carefully using this missing information from one-dimensional case with the special structure of our random field. So it was possible to show such a thing, that there is no global phantom distribution function, but there is a phantom distribution function along some the most important case when we go to infinity with all coordinates. In fact, and this is the content of this paper, in fact, that if we are able to obtain, for example, such information, then we know much more than only the definition provides. And this is the result. We can formally introduce some neighborhood of a monotone curve. You have formal definition. I will have a picture in a moment. But what is important, if the curve is increasing in some cone, and this is the condition here corresponding, then such a curve belongs to this neighborhood. But of course, there are more than only such curves here. We have such a picture. So these are the points, and they are corresponding spaces to which curves, monotone curves from the neighborhood they have to take part. And we can define the phantom distribution function, directional, and admits a continuous function along some. Then it is equivalent. It implies much more, that admits the same continuous phantom distribution function along every curve from this neighborhood, and some technical conditions that we need some convergence, non-decreasing sequence, but on the sequence, it is important sequence of levels, not a field of levels, on the sequence of level, such that we have this convergence and condition previously mentioned is satisfied. So we have a definition that if X admits the same continuous distribution function along every curve, then we say that it admits a psi-directional function. Some comments, such as the phantom distribution functions equal along diagonal. Of course, in 2 dimensions, it's clearly diagonal. In 3 dimensions, it's okay. We understand what is that and so on. Delta directional phantom distribution function is called the sectorial, and our example says that our random field admits a sectorial phantom distribution function, but does not admit any global phantom distribution function. And it should be stressed that this thinking, sectorial thinking, is quite popular. I mean, it's, for example, good. You can, Oleg Klesov is not here, but you can find goods result, law of large numbers in Klesov's book, that we can prove law of large numbers under natural assumption of existence of on the first moment in sectors. So this is something when you consider stronger, when you want to have a law of large numbers only when in the general case where the marginals go to infinity, then of course you have to assume more some logarithmic moment, higher moment is necessary. So this is not surprising, but I must say that people in extreme value theory did not like this idea until we were able to construct an example showing that the directional phantom distribution function is what is in general much easier to obtain, are less general. That means they are more general than the strong global phantom distribution functions. And we come to the final statement related to this idea of random fields. The question is why we cannot transmit this nice one-dimensional theory to the two-dimensional case. And there is a surprisingly simple explanation related to the technicalities. if we have a convergence of monotone functions to the continuous limit on some dense set, that this implies uniform convergence, and we can explore this uniform convergence. If we have random fields and we consider the following function of S and T, yeah, so it's a function on R plus. Suppose it converges to pointwise, I mean to some over some dense set, or even on R plus to this limit, but this convergence does not fall in uniform way. It was Natalia Sawyer who invented a suitable sufficient condition, a condition that allows us to work with at technical level. Okay, the last question is quantum distribution functions on trees. This is really the starting point only. First, we have to realize some difficulties. That there is a very regular structure. We have always, because we can always find a rectangle, bigger rectangle, and so on. So we have some natural monotonicity. The idea is, can we build such a corresponding theory for stochastic processes indexed by trees? In the abstract book, I gave a motivation example. We cannot manage with this example at the moment yet. So it is example mainly because they work with random trees. That means our situation is that we have here, we consider here stochastic process indexed by a tree. And now the next step would be to have a random tree. So for each random path to have, for the time being, we are not able to do that, but something we are able to find. Let's take a rooted tree. Root is R. Then, of course, we know that any point of our tree is connected to the root by unique path. And the length of this path we can call order or number of generation and so on, whatever it means. The meaning is clear. This is the length of the unique path connecting vertex V and R. Suppose we have a stochastic process indexed by V, define the partial maxima over branches. Yeah, but here this is well defined. I mean, we know what does it mean over branch. So for each V, we have only one branch connecting V and R. And again, there is a natural definition for a quantum distribution function. Here we have if we have IID sequence, then we would have exactly equality here with F as the distribution function. But in our formulation, there is no need to consider IID sequence or whatever. We have such a general definition. And of course, to have such a phantom distribution function, we need V to be infinite. We have such a general result. This is the first stage. We have this stochastic process indexed by the tree, admits a continuous phantom distribution function, but it should be phantom distribution function, even only if we use this philosophy, but it is a mixture of conditions. Here we have gamma as the limit, and a non-decreasing sequence of level okay, we see, so it's independent, in fact, on the structure of V, such that this convergence falls uniformly in V as n goes to infinity. So we see if there is some short branch, then of course it disappears here. It's surely 1 in the limit, but also here is in the limit if there is only some finite number of random variables. So it's not surprising to have such a result, but of course not. It's in a sense summary or conclusion from our techniques. Now suppose that branch is infinite. Every branch is infinite. Consider such a branch. We can define a distribution function along B in natural way. And then, of course, we have of course, it is a tree, yeah. So this is they are in the order, natural order, but of course there can be some other outside of this branch. Suppose that a continuous function is a function distribution, a phantom distribution function along every branch. Is it global? The answer is not. So we don't have complete analogy with the lattice case, but if we assume something quite natural condition, but it is a kind of compactness on branches of the tree, that it is not branching too widely. Sorry, for every sequence there exists a branch containing an infinite number of elements of such a sequence, of this sequence. So under this assumption, it's clear, it is easy to construct trees without this property. For such trees, we have that under assumption of compactness property, then we can compute phantom distribution function, provided we can find it along every branch, So this is the moment such a first statement. But once again, I would like to stress we were not able to analyze along this way, the results meant by article mentioned in the abstract book. That means this is much more complicated structure than this one so far analyzed. So that's all what I wanted to say. So I used my. You are hungry? So I use this. I follow this. Because in my case it's 4 after.
Thank you very much.
Thank you.
Any comments, questions?
I didn't catch the definition of MV on the branch or for the generation.
Okay, so this is the definition. This is the definition, global definition of a function, of a phantom distribution function for a stochastic process indexed by V. Yeah.
It's only on the branch.
No, this is everywhere. Yeah, it's everywhere. You see, V only converges to infinity. Yeah. The order of V converges to infinity, then we need such a convergence. So this is the global, once again. But with branches, it has so far it has nothing to do with branches. Yeah, if we
know that the maximum MV is defined.
Oh yes. You are of course. The maximum is over branches, but the convergence is independently of given branch. Yeah, we do not. Thank you for this.
Absolute value is the length of the
Yes,
of the branch.
yes, is the length of the branch. Yeah. So we have such a maxima. You are right over the branch, but for this definition we need convergence, I mean, independently of the branch. It's not along the branch. And of course, the other approach is to be able to compute the quantum distribution function along the branch, because we can do that. So we know how to do that. It's simple in a sense, but then we need some kind of compactness. Okay, so thanks for the comment.
Thank you. I think maybe we should go to lunch. Okay, so thank you very much again.